Alright, we are moving on. We just finished Chapter 5, the stereochemistry chapter, and we're on to Chapter 6. Which is going to be a little more chemical reactivity, properties and reactions, of haloalkanes. Properties and reactions of haloalkanes. What do you think a haloalkane is? Maybe it's a alkane that contains a halogen, so things like bromine, chlorine, iodine, etc. That's what we're going to see. So first thing is the physical properties of these things. Physical properties of haloalkanes. And maybe a good place to start, and these are also called alkyl halides. Alkyl halides. That's another name we often see in chemistry. So a good place to start is the bond strengths. For different alkyl halides. ch6. X would be the halogen, and what we find is that the bond strengths decrease as size of the halogen, X, increases. It kind of makes sense, and we'll explain why in a second. But as you get as the X atom, like bromine, iodine, or whatever, gets larger, then the bond strength gets smaller, decreases. Alright, so let's see a couple examples of this. A methyl or fluoromethane, CF3F. Sorry, CH3F or H3CF. So the bond dissociation energy, which is essentially the bond strength, if we measure that in kilocalories per mole, the bond dissociation energy is 110, which is actually kind of a strong bond. So that's a strong bond. And as you go lower to like chlorine, the bond gets weaker. It's 85. And as you go lower lower on the periodic table, the bond gets weaker, 70. And as you go lower than that, what's lower than bromine on the periodic table? Iodine, and that's 57, so that's even weaker. All right, and then I'm going to erase the I'm going to erase the X here just to make some space. Maybe I'll write it over here. Size of X. X increases, right? Okay. And I'm going to write outer shell of X here. Okay, so the outer shell of that atom, the halogen atom, for fluorine, it's a second row atom, fluorine, so it's 2. And everything else just goes onto subsequent rows. So chlorine is 3. Bromine is 4, and iodine is 5. So each of these are in subsequent rows of the periodic table. Okay, and the one, it does turn out that carbon and fluorine are in the same row, and that might explain why the bond is so strong. It's a very strong bond. 110 is considered a strong bond. Okay, so why do we have this effect? Why do we have this effect? One reason is mismatched orbitals. Now, of course, carbon versus fluorine, those are matched orbitals, so those aren't mismatched. But as you go down the periodic table, fluorine, chlorine, bromine, iodine, the orbitals are mismatched. And that would explain why the bond is weaker. Okay, so if we consider iodomethane versus fluoromethane, and we consider the orbitals, the valence orbitals, on carbon it's 2s, 2p, x, y, and z. Iodine is 5s and 5p, x, y, and z. Okay, and so that is mismatched, right? So the orbitals are not totally, well, they're compatible, but they're not as compatible as with fluoromethane, which also uses 2s, 2p, x, y, z, and the fluorine also uses 2s and 2p, x, y, z. Okay, so that kind of helps explain why fluoromethane has a stronger bond, a more compatible set of orbitals than iodomethane, which has a less strong bond. It's a weaker bond, okay? Alright, another thing about these bonds, and these haloalkane bonds, another thing is that, as you might imagine, the ch6 bond is polarized. Well, that makes sense, because like we know that halogens are further right on the periodic table, so they're going to be a little delta negative, right? So X is electronegative. And so if we think about like fluoromethane, iodomethane. There's a little bit of a partial charge on the iodine, and there's a little bit of a positive charge on the carbon, right? So it's delta positive, delta negative. And as you can imagine, there's going to be some reactivity that goes along with this. So what we're going to do is use negatively charged other molecules that are negatively charged, and they're going to attack the positively charged carbon, and what we'll see is the iodine can be displaced. It'll be kicked off. Okay, so yeah, these polarized bonds lead to reactivity, right? Let's draw another one. So that's 2-bromobutane. 2-bromobutane. What are the partial charges? Bromine is delta something, and carbon is delta something. So the bromine is delta negative, and the carbon is delta positive, right? That carbon there is delta positive, and the bromine is delta negative. And what we're going to see is other molecules, negatively charged molecules, will come and attack and break this off. That's what we're going to lead to in a bit. All right. So yes, the ch6 bonds are polarized, and that leads to reactivity. Some interesting reactivity. Okay. Okay. The other property that we can discuss is boiling points. BP, boiling points. And as you might imagine, the boiling points of alkyl halides are greater than alkanes. So that electronegative halogen atom can actually help increase the boiling points a little bit. So let's show some examples. Methane, the boiling point in degrees Celsius, and it's methane has a very low boiling point. It's negative 161 degrees Celsius, so it's very gaseous at room temp, right? Fluoromethane is negative 78.4. So definitely a higher boiling point. And then chloromethane is negative 24.2. So as these atoms get larger, it looks like the boiling point increases. Bromomethane is 3.6. So at 0 degrees Celsius it's actually a liquid, right? And then iodomethane is 42.4. Okay, so that's actually a liquid at room temp. So which of these would be the easiest to work with, like in the laboratory? Probably iodomethane, because it's actually a liquid. These ones are gases at room temp, and so it's, you know, room temperature is 25 degrees Celsius, right? So yeah, in the laboratory we love to use iodomethane as a chemical reagent because it's actually a liquid. Okay, and also a couple more. Let's do butane and the boiling point in Celsius. Butane is negative 0.5 degrees Celsius, boiling point. Fluorobutane is 32.5. So it's actually definitely a liquid at room temp. Chlorobutane, 1-chlorobutane is 78.4. Bromobutane is 101.6. Iodobutane is 130.5. Okay, so as you increase the size of the halogen, you definitely get a higher boiling point. Okay, so why? Why are when we consider boiling points, why are these haloalkanes or alkyl halides, why are they greater than alkanes? That's a good question. What are the reasons for having, you know, if you have an X, like a fluorine, chlorine, bromine, or iodine, why are those boiling points actually greater than alkanes? Because we see that here, right, in both of these cases. And the answer is probably dipole-dipole interactions. Dipole-dipole interactions. So if you think about like iodine, which is a big atom there. What are the charges around iodine? Well, the carbon is kind of delta positive, as we talked about. The iodine is kind of delta negative, right? Okay, so we got some delta positive, delta negatives. Well, there's another one, you know, there's more of these molecules, and maybe another one will be right down here. And now we got two 1-iodobutanes, kind of talking to each other. This delta plus is talking to this delta minus, and this delta minus is talking to this delta plus. So those are, what do we call them? Intermolecular interactions. Intermolecular interactions. And dipole-dipole interaction is one example of that. Intermolecular interactions. Intermolecular interactions, and that's just, it's one of the examples. We also have like hydrogen bonding and things like that. These can't hydrogen bond because you don't have acidic proton atoms, okay? But dipole-dipole interactions is kind of why the alkyl halides have greater boiling points than alkanes. And then the other question is, why are like alkyl iodides greater than alkyl bromides, greater than alkyl chlorides, and greater than alkyl fluorides. What's the reason for that? Because we didn't explain that. Okay, so there's a couple reasons, and I'm going to try to just sort of summarize them. I'm going to draw these kind of going downward. All right. So as we know, when we have like iodides versus fluorides, iodides have large orbitals, right? Fluorides have smaller orbitals. Okay. Iodides have large orbitals. The fluoride and the fluorine atom has a smaller orbitals. And when you have larger orbitals, you have more diffuse electron cloud. A more diffuse electron cloud. I'll zoom in later. I'm just trying to fit this all on the page right now. Whereas by diffuse I mean like the electron cloud is spread over like a larger atom. But the fluorine atom is kind of small. So if this is diffuse, what does that make the fluorine? What's the opposite of diffuse? It's a concentrated electron cloud. See, the electron cloud is actually concentrated when you consider fluorine. It's concentrated, okay? And when you have a diffuse electron cloud, there's more of a kind of like a surface effect. I'll try to draw that in a second, where basically you get improved London dispersion forces. Improved London dispersion forces. And the London dispersion forces are the same idea as induced dipoles, which is what we're actually these are dipole-dipole interactions. These are a little different. London dispersion are induced dipole. We'll talk about that in a second again. What that means. London dispersion forces. When you have these, this will increase the boiling point. Increase the boiling point because you have more interactions. You have more interactions, you have a higher boiling point. So the fluorine, though, does not have improved London dispersion. There's not like the interactions are not like improved. So we'll say less London dispersion. Induced dipoles. Okay. Alright, I'm going to draw these out in a second. But so far we see iodine has larger orbitals, more diffuse, electron cloud is larger, and more London dispersion forces, which are one of these intermolecular interactions. Net effect is increased boiling point. Okay? And fluorides have less of the London dispersion interactions. And what does that mean in terms of its boiling point? Not less increased boiling point. Okay? Okay, so let me show this a little more graphically now, considering iodides versus fluorides, which we know the iodides have a much greater boiling point, and the fluorides do not have as great of a boiling point. All right. Okay, so example, if I have our iodine, the iodine is a huge thing. The fluoride is a kind of tiny thing, right? Relatively speaking, the iodine's way larger. Okay. And what are the partial charges in an R? R is like the alkyl group, whatever it is. So those are usually delta positive. This is delta negative. This is delta positive. This is delta negative. Okay? Okay, and so the way I usually explain this is that the partial negative charge is diffuse over a big area. So there's a lot of negativity kind of all over the place, over this big surface area. And I sometimes draw that with little, almost like little arrows, like to show that it's over a larger surface area, right? Delta negative diffuse over larger surface area. When you have that surface area effect, surface area, when you have a surface area effect, it actually has more of an effect than in this case. The delta minus is concentrated over small surface area. Okay, a smaller surface area. Okay. Okay, so having this kind of big surface area effect, it just has more of a London dispersion effect, where the dipoles, you know, of this induce dipoles on the other molecules. Okay. All right. And I'm going to give another name for this. This one specifically, with iodide, we're going to call this polarizability. So when you have a huge atom like iodine on a molecule, so it's like, we'll just say like bromide, or, you know, 1-bromo iodine, huge atom, right? The huge atom and the diffuse charge density on iodine, we call it polarizability. We're going to use that word over and over later. And it always has to do with large atoms. Fluoride, this is not polarizable. It's not what we call polarizable. All right. So, yeah. All right. So when we think about polarizable atoms, it's usually going to be things that are lower on the periodic table, like iodine, sulfur. We'll see. Sulfur is a little lower on the periodic table. We're going to see that and call it polarizable also, because it's a large atom with a diffuse electron density. Okay, so kind of remember the word polarizable. Okay. Alright, so next we're on to topic number 2, which is a pretty critical chemical reaction that you're going to see almost through the end of Organic 1 and the end of Organic 2. It's a very important reaction. It's called Nucleophilic Substitution. Nucleophilic substitution. And I'm going to tentatively give this an abbreviation called SN2. Okay. So this is a reaction between something called a nucleophile, which is typically going to be delta negative, and an electrophile, which will be delta positive. It's going to be a reaction between a nucleophile and an electrophile, which is delta positive. We just saw some delta positive things just a second ago, right? It might be the carbon that is carrying halogen, like a carbon with a bromine or a carbon with a chlorine or something. So it's going to be a reaction between a nucleophile and an electrophile. All right. So a couple simple examples. Nuc will be some kind of nucleophile. Lone pair. Draw the lone pair. I'm going to react it with some alkyl halide or haloalkane, Rx. And the charges on the haloalkane, what are they? Something's delta negative and something's delta positive. We usually say the X thing is delta negative, and the R thing is delta positive. And so the reaction that occurs is that the nucleophile is going to attack the carbon, the electrophilic carbon, and it's going to kind of kick off the X thing. Okay. So I'm going to draw the arrows, the mechanism, the electron pushing mechanism, and I generally recommend that you circle the lone pair. If you got a lone pair, circle it. It helps you avoid the mistake of drawing the arrow go the wrong way. And if you circle lone pair, the arrow begins at the circle. It attacks the carbon and kicks off the X group thing. And what's the product? Well, if nucleophile had a lone pair and lost its lone pair, what's the charge on nuke now? It had a pair of electrons and it was neutral. Now it gave up its electrons to make a bond. What's its charge now? And also X minus, because the X took its electrons, it's usually gone now. It's got 4 lone pairs on it, right? There were 3 lone pairs, I'm not drawing them, but now there's 4. But what's the charge on nuke? It's got to be positive. The charge is positive. Okay? Alright, and another option that we sometimes see is when you actually have a negatively charged nucleophile. So here the nuke is neutral, but what if we have a negatively charged nucleophile? So I'm drawing a little negative sign. It's a negative charged nucleophile. So this time the nucleophile starts negative, and then we do the same exact thing. Rx, same thing, delta positive, delta negative, and the nuke now can attack and now what's the charge of the product? Because now you also have nuke R. But if the nucleophile was negative initially and it loses its negativity by the lone pair attacking and making a bond, what's the charge now? Here is neutral, it became positive. Here is negative and it becomes neutral. So now nuke R is neutral. And then we also got this thing. X has been displaced. X has been displaced and now it's negative. Okay. So a couple names of things. This thing left the molecule, right? I drew the arrow on the bottom in this case, on the top in this case. That's all irrelevant. But X left. What's a good name for something that leaves? We're going to call it the leaving group. Or LG. Leaving group or LG. Also a popular cell phone company. My phone's an LG. Alright, and okay, that's the leaving group. This thing you might call the product. It's a product of a reaction. The thing that gets attacked is called the substrate. I guess I have in my notes that it's Latin for subtractus. Subtractus is Latin for to have been subjected, to have been Subjected. So it was subjected to a chemical reaction, substrate. Okay? Alright, and then this thing is the nucleophile. The nuke is the nucleophile. Okay, so this is the general reaction. Alright, so now let's show a bunch of examples of these reactions. Okay, so we know the basic idea of nucleophilic substitution. Nucleophile attacks a substrate, kicks off a leaving group, and you get the product. Let's show some examples now. So lots of examples. Lots of examples. I think there's a table 6.3 in the textbook, so you can see our examples and more examples and tons of examples. Alright, so what I'm going to do is list the nucleophile kind of on the left. Nuke is the nucleophile. It's going to be on the left. And then we're going to have the substrate next to it. And we're going to have the product and the LG. What does LG stand for? The leaving group. Okay? Alright, so let's show a couple examples now. HO. What's the charge of HO? HO is hydroxide. It's negative. If you do the formal charge calculation, it's negative. And let's do chloromethane. H3CCl, chloromethane. And what is the product? So if you imagine hydroxide, OH minus, attacking this, kick off the chloride, what's the product? So that's the nucleophile, attacks the carbon, kicks off the chloride, and you get methanol, methyl alcohol. What's your leaving group? Cl minus. I'm going to skip all the lone pairs, but of course you have 4 lone pairs in chloride. Okay? What if we react, and also remember if you look above, we learned that if you have a negatively charged nucleophile and the substrates are neutral right now, but if it's negative, then the product is neutral and the leaving group is negative. The big thing is you have balance of charge, right? Negative plus neutral gives you neutral plus negative, right? Alright. If you have if the charge isn't balanced, then you messed up. Okay, let's show methoxide, which is methyl O minus, methyl O minus. So that's methoxide. If you want to write that, you don't need the name though, of course. Methoxide, methoxide is this negative charged version of methanol. And what if we react this with iodoethane? Okay, and I'll sneak in the mechanism, the electron movement. I'll do that on the top first. So we circle this and we attack and we kick this off, right? 2 arrows. The attack and then the breaking of the leaving group. Let's do that here also. So circle lone pair, attack, kick it off. I'm trying to draw the second arrow is kind of in the middle of the bond, and this is attacking the delta positive carbon, right? So up here it's delta positive, delta negative. Here it's delta positive, delta negative. I'm just not showing that because it's going to be too congested. But yeah, we're a negatively charged thing is attacking a positively charged carbon, right? Partially positive charged. Okay, what's the product? What's the name of the functional group in the top reaction? What's that functional group called? You should know that. It's alcohol, right? What's the name of this functional group? Carbon, oxygen, carbon. What's that called? It's called the ether. Remember ether? So you actually just learned how to make ethers. This is one of the very standard ways to make ethers. You can almost make any ether in the universe by taking a negatively charged alkoxide. Alkoxide is also this thing with like an alcohol but with a negative charge. It's called an alkoxide. If you have an alkoxide and like a properly substituted alkyl halide, like ethyl iodide or iodoethane, you can make ethers. Okay, let's keep going. What do you think will happen if we take S, 2 carbons, negative charge? So that's it's called thiolate. The names of these things aren't that important. I call that alkoxide. This is called a thiolate. It's just a negatively charged sulfur. Okay. And what if I react this with isobutyl iodide? Isobutyl iodide. What do you think the product's going to be? Well, the sulfur is going to attack. Let's sneak in the delta negative and the delta positive. We got our delta negative, we got our delta positive. Let's sneak in an arrow too, throw in the mechanism arrow, right? Negative attacks positive. And what's the product? Let's draw the product. So it looks like it's going to be 2 carbons sulfur connected to the isobutyl group, right? What's the leaving group? I minus. What functional group did we just create? It looks like an ether, but it's got sulfur. What's it called? It's a sulfide. So, in 2 minutes we just learned how to make alcohol. One of the ways we can make alcohols, ethers, and sulfides through nucleophilic substitution. Let's see what other things we can create. Take cyanide, Cn minus, cyanide anion. Cyanide anion. Well, that's a good nucleophile too. Let's react this one with... I'll zoom out again when I'm done with this slide. But that's bromocyclohexane, right? Let's draw in the delta charges. Delta negative, delta positive. Right. You can draw it larger on your page. I'd recommend drawing it nicely so you can see everything. But the carbon is delta positive and the bromine is delta negative. So where is the the cyanide going to attack? The cyanide is going to attack the carbon. And to draw this, and notice how I'm using a second color. I'm using kind of purple right now. I'd recommend when you're doing all these, you have some sort of second color. It attacks the carbon, right? It doesn't well, you can imagine that it can attack the carbon. It probably attacks it from the top or the bottom or something, but I'm just drawing the arrows sort of go through the bond. Of course, it's not going through a bond. It's probably attacking from the top or bottom. But what's the product? Ah, okay. And what's the leaving group? In this case we used bromide, so the leaving group is bromide, Br minus. Okay, very cool. We just made another functional group. This is another example of making a different functional group. What functional group did we create? I'll give you a hint, it's not cyanide. Cyanide is what we started with. This is not a cyanide or something like that. But this has a name. If you look back on your functional group name sheet, this is a nitrile. Nitrile is a functional group that contains a C triple bond N connected to carbon. Okay? What else do we got? What else do I got? Alright, so notice all of these cases, it's like negative plus neutral makes neutral plus negative. 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 We have conservation of charge. Okay. Now I'm going to do a slightly different one. I'm going to do H3N. That's neutral. These are all negative. This is neutral. Okay, so it's going to be a little different. Let's do 1-iodopropane. Neutral. Yeah, NH3 is a good nucleophile. And ammonia. That's ammonia. And delta negative, delta positive. The carbon is delta positive, right? And where's that nucleophilic lone pair going to attack? This is nucleophilic. Nitrogens are nucleophilic often, and so it's going to attack the carbon. So circle the lone pair, attack, break it off. What do we say? If you got negative plus neutral, neutral plus negative, but this is neutral plus neutral, then you're going to have something positive and negative, so it's going to balance the charge that way. So this thing is going to be positive now. So that thing's positive because what's the charge? Nitrogen bound to four things is always positive. And now we have iodide. Right? Neutral plus neutral makes positive plus negative, and that's how it balances out. Okay. One more example. Phosphorus does the same kind of thing. Phosphorus, trimethyl. It's called trimethylphosphine. Trimethylphosphine. You don't have to know these names, and that's ammonia, which you probably should know, but I'm not going to quiz you on that. Okay, trimethylphosphine has a lone pair. With that lone pair, do you think it's going to be a nucleophile or something else? Yeah, it's totally another nucleophile. So this is yet another nucleophile. And let's do 2-bromopropane, butane, 2-bromobutane. I'm not going to show the delta minus, delta plus. You can fit it in, but yeah, totally. Attacks. What do we got now? Phosphorus, methyl, methyl, methyl. Br minus. Okay, what charges are missing? Well, I show Br minus, but obviously I could never have neutral plus neutral makes neutral plus minus, because the charge wouldn't make sense. This is going to kind of act like the above one. So now phosphorus is what charge? It's going to be positive. And if you do the formal charge calculation, you'll see it's positive. Okay? So we have phosphorus with a positive charge and 3 methyls on it, and then is attached to butane at the 2 position. Okay? Okay, a couple other things. We have this huge sheet now. All of these are called, all of them are called the Snt reaction. All of these are examples of what we call the Snt reaction. We'll talk a ton more about the Snt reaction. So there's lots to know about the Snt reaction. But these are all proper, correct examples of what we're going to call the Snt reaction. All right, they're all pretty easy to visualize, and in each case, the nucleophile attacks, the substrate kicks off the leaving group, and you get a product. Okay. The other interesting thing is that these ones, and these ones are slightly different. What's the difference between the top series and the bottom two? the top series, you have a charged nuke. Charged nucleophile, right? All of those are all charged nucleophiles, negatively charged nucleophiles, and these ones are neutral nuke. So neutral nucleophiles, and the only difference between those is that the it kind of changes the charge of the product. With the charged nucleophiles, you get neutral products. With the neutral nucleophiles, you get charged products. But in all cases, the charge on the left matches the charge on the right. Okay? Alright, a couple more reactions. I'm going to put a line because these are going to be a little different. I'm going to say versus. If I have iodide I minus, so it looks like a nice charged nucleophile, I minus, and I react it with tert-butyl bromide. I get tert-butyl iodide and Br minus. Okay. This is not an Sn2 reaction. I'll give you a name of this, but this is actually next chapter. The big thing is that when you have a tertiary substrate, so that's a substrate, right? These are all substrates. It's tertiary. Tertiary substrates do not undergo Sn2 reactions. Okay, let me just draw another one real quick. Br minus. Nice tertiary substrate. It does give the product that you might expect. But these are actually, unlike the ones up top, which are the Sn2 reaction, these ones are called the Sn1 reaction. These are called the Sn1 reaction, which is next chapter. Chapter 7, I think it is. Yeah. Okay, so and the other thing I'm going to say is, you know how we have our nice little arrows up top for the Sn2? Well, these arrows are different. I'm just going to write weight on mechanism. Weight on mechanism. Exclamation point. Weight on mechanism. A little bit of preview, you know, this will be next chapter, but the mechanism of these is not just like nucleophile attacks. What actually happens is the leaving group first goes away. The leaving group just departs, takes off, and then the iodide, and then you get a carbocation. You'll have a carbon with a positive charge, and then the nucleophile attacks. It's almost like a 2 or 3 step process. So that's what the Sn1 reaction is going to be. That's really next chapter. We have a lot to talk about the Sn2 reaction, but notice though that these are tertiary substrates. Tertiary substrates do not allow Sn2. The tertiary substrates do not allow Sn2. Okay? And so in this chapter, we're really going to focus on Sn2. And the big thing about Sn2 is that the substrate is either going to be methyl, like ch6, it's going to be primary, or it's going to be secondary. but never, ever, ever tertiary. Tertiary will never undergo Sn2. Okay? And then the other thing is next chapter, we'll focus on a couple of reactions, not just Sn1. But we're going to talk next chapter about Sn1, E2 and E1. I'll just give those. I'll mention the names now. I'll explain them later. Next chapter is going to be something called Sn1, E2, and E1. All right. That's all. Next chapter, and those are cases where the substrate is usually going to be tertiary, and sometimes it'll also be secondary. And we're going to see it's going to be a little confusing. That the substrates can be different. So there can be like a couple different substrates for each of the reactions. It will be a point of confusion, but fortunately, that is next chapter. So right now, it's not as confusing. Okay, so we'll get to all that confusing stuff. All right. One thing about Sn2 reactions in Sn2, which is kind of what we're talking about this chapter. The nucleophiles are either going to be strong bases, which are like carbon O minus. That's going to be an example of a strong base. We just saw that kind of thing just a little bit ago, right? We even gave it a name. Let's write down the name again of these kind of strong bases, because it kind of looks like an alcohol, right? If that was an OH, it'd be an alcohol, but it's not an alcohol. It's a carbon O minus, and this is called an alkoxide. This specifically might be called methyl alkoxide. Yeah, methyl O minus or methyl alkoxide. So you're going to hear that name from time to time. The other things that are kind of common nucleophiles in Sn2 reactions are weak bases that are highly polarizable. Weak bases that are highly polarizable are also going to be kind of good nucleophiles, and I minus is one of those. Terrible base. It's not a strong base. This is relatively speaking, this is a much stronger base. But things that are highly polarizable are wonderful nucleophiles, as we're going to learn. The other things that are highly polarizable, you know, what did we say are the polarizable things, or lower on the periodic table? So, for example, like sulfur with a negative charge on it, that's a wonderful, highly polarizable nucleophile. Wonderful Sn2 nucleophile. Very weak base, highly polarizable. So, what's underneath sulfur? You look on the periodic table, you'll see selenium. Also, an amazing nucleophile. Amazing nucleophile. Very, very, very polarizable. It's a huge atom with electron density dispersed all over the place. Amazingly powerful nucleophile is sulfur minus, selenium minus, you know, iodide minus, also very good nucleophile. Okay. Okay, so let's talk about number 3 now. Reaction mechanisms. Reaction mechanisms, kind of as a general topic. Reaction mechanisms, and also this concept of electron pushing arrows. Okay, so we showed that Sn2, the mechanism, right? right? We have a X minus or something negative that attacks the positive charge with the carbon on it and makes the product. That's actually a mechanism, but there's other kinds of mechanisms, and we just want to kind of talk about them kind of generally. So recall, first let's just recall radical halogenation. Remember radical halogenation? That was the first reaction you learned about. So it was described in detail in terms of the mechanism. In a detailed mechanism. What are the steps? I'm not going to review it, but we have names for them. Let's just review the names, right? There was initiation, prop 1, prop 2, termination. They had magic words. We have not had a magic word in a bit. We will have more, so don't be. They'll come back. So be ready for it when I say the magic words. But these did have magic words associated with them. Okay. And what kind of arrows were they? These were these kind of arrows. They're radical arrows. They were called fishhook arrows. Fishhook arrows. What was special about a fishhook arrow? We call them one electron arrows, or one electron movement. And like I said back then, and you probably have forgotten, very little of our course, Organic 1 and Organic 2, is you can use fishhook arrows. So you start off learning about fishhook arrows, and then don't see it again for a good while. Near the end of Organic 2, you might see fishhook arrows again. So the fishhook arrows again are like that, and those are single electrons. So this is a 1 electron. What are a 2 electron arrow is kind of like this. So most of the rest of the course are like 2 electron arrows. Okay. Yeah. Anyway, also, you know, that was your first mechanism. It was a complicated mechanism with 4 steps, right? What about also acid-base reactions, right? That's also a very simple mechanism, a very, very simple reaction mechanism. So if I have like water, and water reacts as a base with HCl, what's the product and what's the mechanism? So water as a base just rips off a proton, and so I can circle this and attack this and kick this off, and you form hydronium, right? And you make Cl minus. What's the charge of hydronium? Of course, neutral plus neutral makes something plus chloride, which is positive. So neutral plus neutral makes positive plus negative, and that balances out. And so that's a simple example of an acid-base reaction. How many arrows? It's 2. Oxygen grabs the proton, breaks the bond. Yeah, and you make hydronium, right? Okay, so the arrow starts at electron density, like a lone pair. The arrow is always in these kind of 2 electron mechanisms. The arrow always starts at electron density, which means a lone pair usually, and it ends at, or it goes towards what? What's the opposite of density in this case? Electron deficiency. Deficiency. So usually from electron density it's delta negative, and electron deficiency is delta positive. It goes from electron density, delta minus, towards electron deficiency with delta plus. And we saw that in like the 10 examples we just did on the previous page, right? All of those examples of Snt reactions, okay? I'm going to show a couple more examples of mechanisms real quick now. So just more examples. The first one you already basically saw already. Hydroxide is a nucleophile. We'll use chloroethane as a substrate. This is nucleophilic substitution. Nucleophilic substitution. Product is incredibly easy. It's delta minus, delta plus. Circle lone pair, attack, break the bond. You make ethanol. Ethyl alcohol chloride. Okay. Other examples. If I have tert-butyl chloride, and we already talked about how that does not undergo SN2, right? But I did give you a hint of what does happen. And what we'll learn is that on a tertiary carbon, the leaving groups can just dissociate, just fall off, without any help. Just fall off. And that's called dissociation. Dissociation. What do you get when the leaving group just falls off and it dissociates? What's the carbon look like now? Well, it looks kind of like that. That thing's gone. Chloride was negative. What's this thing now? It's got to be positive, right? And that's called a carbocation. Carbocation, okay? And the charge always goes towards the electronegative thing, which is the leaving group. Chloride's the leaving group, dissociates, kicks it, falls off, and you get a Cl-, okay? And the reason I'm doing this is to give you other words for things other than substitution. Substitution is like one thing substituting for another. Dissociation, something's dissociating. What about addition? So if I have OH minus, I'm going to draw acetone, which is ketone. Dimethyl ketone. Addition. Addition is going to mean A plus B makes C. It's just going to attack and just attach. So what am I going to do? What's my charges on the ketone? What's oxygen? Delta on the periodic table. It's a little on the negative side. Delta negative. What's the ketone carbon? Delta positive. What do you think negative charge OH minus is going to do? It's going to attack the delta negative. But there's no leaving group, it just pushes on to the oxygen, right? And that is called addition. And now we have H3C, CH3, O, OH, dot 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 dot. Okay, the OH was negative, now it's neutral, but then the other oxygen's negative, right? Because it's got, we pushed electrons onto it, so it was neutral, now it's negative. Negative plus neutral makes negative, right? That's called addition. I'm going to show one more example of addition now. But generally speaking, what do you think addition means? It's like two things that combine make a third thing, right? Okay, so another example of addition. It's just an alkene, right? We have a double bond, okay? Double bonds have a pair of electrons, and that pair of electrons can attack stuff, so like a proton. So this is going to be a weird one where the double bond thing is going to be a nucleophile, the H plus, which is a positively charged thing, that's going to be the electrophile. Sometimes I call the electrophile E plus. So this is the nuke, this is the electrophile, this is the nuke, this is the electrophile. So what happens here? This one's a little weird, but it's also an addition. Well, nucleophile just attacks. And so here it's the double bond attacks. It's kind of a weird idea, but we're gonna see a whole chapter later near the end of this course where alkenes act as nucleophiles. It attacks things, electrophiles, right? Well, what do you get when this plus this forms this? So, of course, how many carbons is it going to be? Well, it's 3 plus 3, 6. It's still going to be 6. That's going to be kind of the structure of it. But this neutral plus positive should make this be, the whole molecule should be what charge? Neutral plus positive makes positive. So there has to be a positive charge thing, and it's actually right here. And what do we call this thing with a carbon with a positive charge? A something cation. It's another example of a carbocation. Okay, so this just shows all of those four kind of examples of, you know, nucleophilic substitution, or you could just, I mean, generally speaking, substitution means A plus B makes C plus D, right? Dissociation, A makes B plus C. Something dissociates, right? Addition, A plus B makes C. Here's another addition, A plus B makes C. So this just shows and gives names to the different kind of electron pushing mechanisms that we will see 1,000 times through Organic 1 and Organic 2. There's tons of these examples. We're going to learn about substitutions, dissociations, additions. There's going to be also something called elimination. I'm not going to show that this second. Eliminations are another kind of reaction we'll talk about too. Okay, cool. Alright, so a couple little things will be done for today. Moving on to topic number 4. We're going to continue back to nucleophilic substitution. And talk about the kinetics of this reaction. Kinetics. So the speed of the reaction. And it's a pretty simple idea. Let's just consider a simple reaction, a simple example of nucleophilic substitution. If we react with like hydroxide with chloromethane, you should be able to draw the mechanism and the product, of course, delta minus delta plus, and yes, so OH minus attacks the carbon and kicks off the chlorine, as we've discussed about 1,000 times now. Now we make methanol and we make Cl minus. Okay, so that's a simple example of this reaction. Okay, so we can observe the rate, of the reaction, and that'll give us some hints on the mechanism. We can observe the rate of reaction by two methods. We can observe the rate of the reaction by two methods. The two methods are monitor the consumption of the starting materials, monitor consumption of the starting materials. So like we can watch the starting materials disappear. of the starting materials, there's ways to observe like organic molecules, like chloromethane, easily. It's maybe a little easier to monitor this than it is to monitor this. And so I'm just going to mention a technique called gas chromatography. Gas chromatography, or GC. You might hear about that in a lab class or something. Gas chromatography is a way to kind of analyze the amount of organic molecules, especially volatile, small molecule volatile species like chloromethane or methanol. Alright, so we can monitor the consumption of the starting materials, or we can monitor the what of the products. Monitor if we're consuming starting material, what are we doing to products? We're producing them, right? We can monitor the formation of products. We can monitor this stuff going away or this stuff forming, right? Alright, so experimentally we do this, and this is a pretty straightforward procedure. Experimentally it's found to be the rate is equal to K, which is a constant, times the concentration of substrate times the concentration of nucleophile. Okay? The units are moles per liter times seconds over inverted seconds, seconds to the -1. So it's moles per liter per second. So it's a unit of time, right? Yeah, as you imagine, rate is something by divided by time, and it's moles per liter divided by time. Okay, so that's the rate. So thus, the rate depends on how many chemical quantities. The rate depends on both starting materials. Both starting materials. The rate depends on both starting materials. Okay? And that suggests the mechanism involves, not only does it involve both, involves both reagents, not only does it depend on both, but it depends on both in a single step. In a single step. But we already showed that, so that's not exactly news. We already showed how the nucleophile attacks the carbon and kicks off the leaving group. So this isn't like crazy news for us. We already kind of know that both reagents are involved in a single step. Okay. Now, what would the effect be if I say I'm doing this reaction? You know, chloromethane and hydroxy, just like we showed it up here, right? There it is. So hydroxide attacks chloromethane, and we make methanol and chloride. What would the effect on the rate be if I say I double the amount of this? Would the rate stay the same, or what would happen to the rate? If you double this, what does the rate do? It doubles, right? What if you double the amount of hydroxide? Well, then it doubles also. It depends on both of these things. So if you double this, this double. If you double this, this gets doubled. What if I double this and double this? Then the rate should be quadrupled, right? So it depends on both starting materials. Okay. And I'm just going to finish up with one little thing. Okay, so both starting materials are involved in a single step. The mechanism, when both starting materials are involved in a single step. The mechanism is called, anybody know, is it unimolecular or bimolecular? It's involved in two reagents, so maybe it's called bimolecular. So it's a bimolecular reaction, and the rate depends on how many reagents? 2 reagents, both starting materials. And the reaction is named, was it named? The reaction is named SN2. And the N is a little bit subscripted, if you can do that. Okay, so SN2 means substitution nucleophilic bimolecular. Substitution nucleophilic bimolecular. Some people say biomolecular, like biological, and that's false. Nothing to do with biology. This is just a general chemical reaction. Bimolecular, not biomolecular. Okay,